Okay, now we're going to look at the force equilibrium method. It says procedures because there are some variations of this based on some assumptions that we'll talk about. Probably the most distinguishing feature of the force equilibrium procedures is they can be used on non-circular failure surfaces. And as the name implies, there's no attempt to satisfy moment equilibrium. We are only satisfying force equilibrium. Non-circular surfaces are quite useful for cases like this. Maybe you have a thin, weak seam, and maybe effective stress conditions apply everywhere else, but this is a saturated clay seam where you have phi equals 0, undrained conditions, and so if you just do a circular surface, it would just barely touch that, but with a non-circular surface, you can have a big part of the failure surface go through that weak material, which often gives it the lowest or most critical factor of safety. So, with the force equilibrium method, in this case, for the side forces, we're showing a resultant force Z and an angle at which that's applied, theta, on each side. And so we're not satisfying moment equilibrium, so the location of Z and the location of N don't matter. Those only matter if you're doing moment equilibrium. And so our unknowns are one factor of safety, N values of N, and then N minus 1 values of Z and theta. So a total of 3N minus 1 unknowns. We have our equilibrium equations. We have N equations for summing the forces in the vertical direction and N equations for summing the forces in the horizontal direction, or 2N. And since 3N minus 1 is greater than 2N, we have to make N minus 1 assumptions. And the simplest thing is to assume N minus 1 values of that side force inclination theta. So and we're going to talk in a minute about what kind of assumptions you make on that, but assuming you've assumed something for that inclination, then we proceed to the main computation stage. And step 1, you assume a factor of safety. So this is an iterative method. We have to guess at a factor of safety and then solve for a factor of safety, and then continue until our the factor of safety we calculate is equal to the one we assume. And so once we've done that, we can, once we've assumed a factor of safety, we can come up with our mobilized cohesion and our mobilized friction. And then we look at a slice, and we're going to start on the left side and move to the right. So this, on the left side, the leftmost slice is a triangular wedge, and the forces on the bottom are N prime tan phi prime, or the mobilized friction, and the mobilized cohesion times delta L. And acting perpendicular to that, we have the effective normal force and then the pore pressure U delta L. We have the weight of the slice, and then on the right side we have the ZI, and then there's also an angle at which that applies, which we've assumed. So we have two sets of equations. We can, on this free body diagram, we can sum forces in the x direction and in the y direction, and we have two unknowns. The two unknowns are N, or N prime, and Z. Everything else is a known term. And so we solve for that, and then once we know ZI, that same ZI will be applied to the slice to the right, but in the opposite direction. So here we go, we found ZI, and then we apply that to the right. Then we solve the free body diagram for the next slice to the right. And in this case, again, there are two unknowns, N and ZI plus 1. So we use our force equations in the x and y direction and solve for N and ZI. And then we just repeat this and propagate to the right. And we get all the way to the last slice, which is again a triangular wedge. Z is known. The only unknown is N. So now we have two equations and one unknown. So we just check to see if the equations balance, if the forces balance out. If they do not, then we try a new F and repeat all those calculations. Of course, you'd want to automate this, and you could do it in Excel. You could do it in source code and in slope stability software, and then you just iterate until the assumed F matches the computed F, and that's your factor of safety for that configuration. Now, I mentioned that you have to assume a side force inclination. There are different ways to do that. For the Lowen-Karafaith method, for each slice, use the average slope of the ground surface and the slip surface. So you look at a slice boundary and you look at the slope of the ground surface at the top and then the slope of the bottom of the slice, and then average those, and that gives you I think it's probably the best of these assumptions personally. The simplified Yan-Bu method just assumes all the side forces are horizontal. And then there's a Corps of Engineers method, which assumes the forces are parallel to the slope. And there are different ways to determine what that slope angle is. You can have a single angle shown in the top two diagrams, or you can just take the average slope angle at the top here and apply that to the inner force slices down below. It's also sometimes called the modified Swedish procedure. So, summary, the force equilibrium methods work both on circular and non-circular surfaces. Satisfy force equilibrium only, not moment equilibrium. It does require some iteration, and our key assumption is what angle do those side forces act at.